Hey everyone! Today I want to talk about a special class of materials called glass ceramics. As the name suggests, these materials are neither pure glass nor pure ceramic, and they can have some pretty unique properties. There are many different types of glass ceramics, and each type is generally tailored to a specific application. Glass ceramics like Zero-Dur, Clear Ceram and Ulay are engineered to have a high dimensional stability under temperature changes, making them very suitable for use in, for example, metrology instruments, semiconductor equipment and precision optics. However, glass ceramics are not just found in high-tech applications. Ceram, Robex and Corningware are widely used in household items like cooktops, shields for fireplaces and ovenware. Now, you'll probably expect me to talk mainly about materials that are specifically designed for optical applications, but I will actually focus more on the household ceramics because these are very accessible to everyone and at the same time have properties that are quite similar to the high-end materials. And what most people are unaware of is that you can also polish Ceram and Robex to a pretty nice optical finish. The invention, or should I say discovery of glass ceramics in 1953 was actually kind of accidental. Donald Stuckey, a researcher at Corning, was working on a photosensitive glass called photoform. This glass contains, among a photosensitizer, additional aluminum oxide and lithium oxide and can be structured directly using photolithography and etching. Stuckey came to the lab one morning to check on an experiment and found that the temperature of the oven was accidentally set to a value that was too high, 900 instead of 600 degrees Celsius. So he expected the glass in the kiln to be completely molten by the high temperature. But to his surprise, the glass was not a liquid. Instead, it had transformed into a milky white opaque material, and it turned out to be very resistant to thermal shock. Stuckey immediately recognized the potential of this material, and this was the start of research that led to the development of Pyroceram and Corningware as commercial products. To illustrate how resistant glass ceramics are to thermal shock, I want to show you a simple experiment. This is a strip of window glass, which I will heat up in a flame to about 300 to 400 degrees Celsius, and when I dip this hot strip of glass in cold water, thousands of small cracks form in the material. So here the thermal shock completely destroyed this sample. And we can do the same thing with borosilicate glass, which is a bit like Pyrex. It's way more resistant to high temperatures and thermal shock than soda lime glass, but something similar happens here. As soon as the sample hits the cold water, we observe the formation of cracks that propagate into the sample. There are definitely less cracks in the borosilicate strip, but even this glass cannot resist the harsh treatment. Now watch what happens when we do the same thing to a strip of a transparent glass ceramic called Robex. Here we go. You observe that essentially nothing happens to the material and there is not a single crack visible after the experiment. We can make it quite a bit more challenging and heat the sample until it's red hot, meaning that the temperature is likely over 600 degrees Celsius. But even then, the thermal shock introduced by cooling down to about 10 degrees Celsius in only a few seconds does not pose a problem to this material. And you can repeat this procedure 1,000 times and nothing will happen. Now personally, I think this is totally amazing and it illustrates the remarkable thermal properties that some glass ceramics have. In the last few minutes I've been using the words glass and ceramic without any explanation. So glasses are generally transparent materials and have an amorphous structure, meaning that the molecules are not very ordered. Basically, the molecular structure of a glass looks like a frozen liquid, and indeed a glass is what you get when you cool down a liquid state too fast to form crystals. A ceramic, on the other hand, is produced from crystals and is usually formed from sintering inorganic crystals together at high temperatures. And each of these crystals contains a high degree of order. So not only do the two have a completely different structure on a microscopic level, they're also manufactured in very different ways. Glasses are produced from a melt, whereas ceramics are produced from small crystallites. Now, as will be explained later in the video, glass ceramics combine a glass phase and a crystalline phase in the same material because the crystalline phase is produced from the glass phase. Robex is a transparent glass ceramic that is used in, for example, screens for fireplaces. It's actually quite cheap and it's extremely resistant to both high temperatures as well as to temperature shocks, as I've just demonstrated. So why do standard glasses break? Well, it's actually because of two things. Like most materials, standard glasses expand when heated, and on top of that they are quite brittle, which means that they are hard and stiff but not very strong. Now, the breaking of the glass, as demonstrated, is not about temperature per se. As long as the temperature is fairly uniform in the object, it will not just break. However, when a temperature gradient is introduced in the material, the expansion or contraction can introduce high levels of stress inside the material. Stress levels that actually exceed the mechanical strength of the material itself. So in the experiments just shown, we cool down a sample rapidly from the outside. This leads to a temperature gradient in the glass, especially since it's not a very good conductor of heat. And given that glass contracts when cooled down, this gradient leads to tensile stress in the outer layer and compressive stress in the core of the object. And if the tensile stress that is introduced is higher than the material can handle mechanically, cracks can easily form from small surface defects, which then propagate inwards. Now, why does this not happen to Robax and other glass ceramics? Well, there's a few aspects to this question, but I guess the most important aspect is that they have an extremely low coefficient of thermal expansion, CTE for short. So imagine for a second a material that does not expand or contract as a function of temperature at all. In other words, it has a coefficient of thermal expansion of 0. In that case, a temperature gradient will not introduce any stress, and in the absence of stress, there is no reason for the material to crack or break. Let's quickly take a look at what the coefficient of thermal expansion is and how you can measure it. In this video, we'll mainly be talking about linear CTE, in other words, the expansion or contraction along a specific axis as a function of temperature. If we have a bar of a material of known length L and we change its temperature by delta T, it will generally change length. And in this example, it expands by delta L, so we observe an increase in length with an increase in temperature. So CTE is the change in length per unit of length per degree Celsius temperature change. CTE is frequently expressed in parts per million per degree Celsius, or Kelvin, which is equivalent to a change in length in microns per meter of length per degree Celsius. So this table contains a few example CTE values. You see that plastics like polyethylene have a rather high expansion of up to 200 ppm per degree Celsius. This means that a bar of polyethylene of 1 meter length will expand by 200 microns or 0.2 millimeters per degree Celsius temperature increase. Pure aluminum has a CTE that is quite a bit lower, 21 to 24 ppm per degree Celsius, and soda lime or window glass has a CTE somewhere between 7.5 and 9.5 ppm depending on the exact chemical composition. Borafloat 33, which was the second glass in the experiment, has a very well-defined value of 3.3 ppm per degree, which is about 3 times lower than standard window glass. And then there is quartz glass, which consists of pure silicon dioxide, which only expands by 0.5 microns per meter per degree Celsius temperature rise. So you see that even between glasses, there's quite a large difference in expansion coefficient. By the way, quartz glass is also particularly temperature shock resistant. Here you see me dip a strip of hot quartz in cold water, which also survives the treatment without breaking. And this again illustrates the importance of a low CTE. But high quality quartz is quite expensive and difficult to make, and it's not as resistant to thermal shock as certain glass ceramics. Here I added the CTE data of a few glass ceramics like Robax, Ceran and Clearceram from their data sheets. And for these materials the CTE is generally specified as 0, plus or minus a specific tolerance. The actual value of the CTE is in the deviation it can have from the 0 value. So apparently the value can also vary between different batches. The CTE of Robax is specified as 0 plus or minus 0.5 ppm, and for Ceran it's actually not even specified, other than that it's near 0. And for Clearceram, a glass ceramic specifically intended for high precision applications, the CTE is specified to be 0 plus or minus 0.1. But in fact, tolerances can be much tighter, especially within a specific temperature interval. This graph shows the relative change in length and the corresponding CTE for a high grade of Zeradur that is optimized for the use at room temperature. And if you look at the CTE here, it's somewhere around 0.01 ppm per degree. So it's about 10 times lower than the value specified for standard clear ceram. Now of course we can take these numbers at face value, but I decided to see if I could measure the actual expansion coefficient of a few of these materials. So to do this, I'm going to use samples that have a length of around 100 millimeters, and this requires that we can measure changes in length with a micron or preferably submicron precision. For measuring the changes in length, I made this tool that can be placed on top of the gauge of my spherometer, which is the Ultra Spherotronic. Sorry, couldn't resist. So this part consists of 2 aluminum rings and 4 clear ceram spacers. Here's a schematic representation of the tool. The idea is of course that the clear ceram has a low expansion of only plus or minus 0.1 ppm, and on top of that remains at more or less constant temperature during a measurement. The aluminum of course does not have zero expansion, but you can make the expansion of the aluminum largely irrelevant by carefully choosing the configuration. For example, by making the clear ceram spacers extend to the connection point of the spacer that points downward. At the lower side we can choose the measurement point such that the difference in the CTE between the stainless steel micrometer gauge pin and the aluminum becomes largely irrelevant. But of course, it's also important that the stainless steel pin does not heat up too much when in physical contact with a warm sample. In a measurement, you uniformly heat up a piece of material with length L to somewhere between, let's say, 50 to 70 degrees Celsius, and then clamp it between the gauge and the clear ceram bar. And it then starts cooling down slowly to room temperature. And we can measure delta L and calculate delta L divided by L. At the same time we record the temperature T, and because we know the length of the piece, we can plot the values and then calculate the CTE of the material from the slope in the graph. The clear ceram spacers separating the 2 aluminum parts were actually cores that were drilled out of blocks that I made for another project. I admit these rods look a bit sloppy in the center, and that is because I had to drill the holes from 2 sides to get them to meet up in the middle, which as you can see was not very precise. But these are not intended to look good. The important thing is that they don't change length during a measurement. So let's do the experiments. For each material I cut out strips of approximately 100 mm long and about 15 mm wide. I've got soda lime glass, borosilicate glass, quartz and 3 types of glass ceramics, Robex, Ceran and clear ceram. I also added a piece of extruded aluminum which can be used as a reference. Now because I wanted to measure the temperature of the strips using an infrared thermometer, I had to add these black areas using spray paint. The reason for adding these is that every material irradiates heat in a different way. So in order to get comparable temperature readings between the samples, you need a standard surface area to measure on. For each sample we first measure the total length, then we'll heat up the sample somewhat, say to 50 degrees Celsius, and then we measure the change in length delta L while cooling down to about 10 degrees Celsius, which is the temperature in my workshop. This is an illustration of the contraction of soda lime glass in real time, which is actually pretty obvious on the display. And during the cooling down process, the temperature is also measured at certain intervals, and these measurements then resulted in the following graphs. We'll start with aluminum. The individual measurements show a fairly linear relationship between length and temperature, which I guess is a good sign. If we measure the slope of the graph, we find a value of 32.4 ppm per degree Celsius, which frankly is quite a bit too high given the generally accepted range for aluminum. So this indicates that our setup may not be very accurate. But before we conclude this, let's take a look at some of the other values. The graph for window glass is shown in blue and results in a CTE value of 9.3, which is also a bit on the high end of what we expect. But I guess it's still within the range that we can expect. So here the experiment more or less matches with the known value range. Now the next glass is Borofloat 33, which has a well-defined CTE of 3.3 ppm per degree. And here the measured value is actually spot on, with a deviation of less than 2%. So this is a strong indication that our setup and measurement method is not doing a bad job after all. I'm not sure why the aluminum rod I used has such a high expansion. It's an extruded rod, so maybe this created some kind of anisotropy in the expansion. Now the last value I want to show you in this graph is quartz. Here I measured a value of 0.6 ppm per degree Celsius, which is in agreement with the approximate value of 0.5 ppm from literature. So in general I would say that the measurements indicate that this setup is working as intended. Okay, so let's move on to the glass ceramics. We'll take the values of quartz as a reference because they are the lowest values from the previous graph and plot them on a somewhat different y-axis scale. Let me now show you the results for Robex. Turns out to have a value of minus 0.5 ppm per degree Celsius, a value that is still within the specified range of the datasheet. So this sample actually shrinks a bit when heated. Next is Ceran, which also has a negative CTE of minus 0.3 ppm. The last measurement is on clear ceram, which resulted in a value of plus 0.2 ppm per degree Celsius, the lowest value of them all in the absolute sense. And if we compare the latter value with the value specified in the datasheet, plus 0.2 ppm is outside of the tolerance range of plus or minus 0.1 ppm, but I guess that here we are actually hitting the accuracy limit of the setup, which I think is in the order of plus or minus 0.1 ppm per degree. Now if we look at the Robex and Ceran samples, from an application perspective, a slightly negative CTE is actually an advantage. During practical use, the highest value of internal stress levels from thermal shock will be encountered when the hot material comes into close contact with a much colder liquid. And a negative CTE would lead to a compressive stress in the outer boundary of the part, which can suppress the formation and propagation of cracks originating from the surface. So how is a negative CTE even possible? Well, earlier I mentioned how the discovery of glass ceramics at Corning involved the presence of lithium and aluminum oxide, and an essential aspect of the invention of glass ceramics is that certain crystals containing lithium, aluminum, silicon oxide can have a negative coefficient of thermal expansion. So you're probably aware that pure silicon dioxide or quartz can form these nice hexagonal shaped crystals like the ones shown here. But if you would try to grow crystals from, let's say, a mixture of silicon oxide and aluminum oxide, you will generally not end up with neat-looking uniform crystals. And that is because the silicon and aluminum ions are largely incompatible in a crystal structure. However, if lithium is added, stable crystals can form again, and these crystals have a rather special property in that they have a negative CTE. Not really sure how this works exactly, but it has to do with the location of the lithium ion in the crystal structure, which is dependent on temperature. Now it turns out that this property is not unique for the addition of lithium. It can also be observed when the lithium is substituted with, for example, zinc, which also yields a material with a negative CTE, or we can substitute zinc with magnesium, in which case the crystals have a positive CTE. This table sort of summarizes what I've just said. Here are the chemical compositions of the crystals discussed. These two columns show the linear CTE along the two important axes of the hexagonal crystal structure, and as you can see, the values are highly anisotropic. This last column contains the volumetric CTE, which quantifies how much a crystal would shrink in volume as a function of temperature, and as you can see, some of these do indeed shrink given that they have a negative CTE. So depending on the chemical content, you can make crystalline materials with a range of CTE values. Now, to make a zero expansion material, you could, for example, start out with a glass that contains the oxides that are essential to creating crystals that have a negative CTE. And that means that the glass must contain silicon, aluminum and lithium oxide, and additionally it can also contain some of the other oxides mentioned. Since this is a glass and not a crystalline material, it will have a positive CTE value. But if we now create the circumstances that produce a sufficient volume of crystals with a negative CTE, we can make these compensate for the positive CTE of the remainder of the glass phase. And in that way, we can create a material that does not change shape with temperature and has a net zero CTE. Now this is actually quite difficult. For one, you need exactly the right concentrations of ingredients and then generate a very specific fraction of crystalline phase with exactly the right composition. But another thing is that crystals don't just grow in glass. They need a point to grow from, which is called a nucleus. So a nucleus can be a small crystal that was spontaneously formed and that was able to reach a certain critical size from which it cannot easily dissolve again. Or it can be some other compound deliberately added that does not dissolve well and easily creates small crystals, which can then act as nuclei for further crystal growth. Now, because we don't want to leave the formation of crystals to chance, a nucleation agent like, for example, titanium oxide is added that can create a homogeneous concentration of these nuclei. So, problem solved? Well, we're still faced with the fact that nucleation and crystallization generally occur at different temperatures. Here is a plot of the crystallization and nucleation rates in a glass as a function of temperature. And you see that the maximum formation rate of nuclei occurs at a lower temperature than where we find the maximum crystallization rate. In this graph, Tm indicates the melting temperature. Above this temperature, the glass is considered to be a liquid and any crystals already present would simply dissolve, hence the negative crystallization rate. Below the melting temperature, crystallization could in principle occur in the glass, but here the rate of nucleation is near to zero. So when you cool down a glass from a melt, there are initially no nuclei to grow crystals from. And this means that we basically have a supercooled liquid in this green temperature regime. Now, if we cool down further, nucleation can start to occur, but here the rate of crystallization has become much lower. So all this means that if we cool down a glass from the liquid state sufficiently fast, we can almost completely avoid crystallization. However, going up from the lower temperature regime, we can first create a certain concentration of nuclei, and when that is achieved, we can increase the temperature further to introduce sufficient crystalline phase with the desired properties. Okay, so that's the theory, but how does this work in practice? Well, you start out with a specific mixture of oxides from this table. As stated, silicon, aluminum and lithium oxides generally need to be present. Magnesium, zinc or phosphorus oxide can also be added and used to tweak the CTE of the total crystalline phase. To this mixture we add a small amount of titanium or zirconium oxide as nucleation agents to help the homogeneous nucleation. There could be other stuff in the mixture like, for example, melting or fining agents to avoid bubble formation or coloring agents to give the material a specific color, but the components in the table at the bottom are not really essential for the principle of zero expansion. In an industrial version of this process, the raw materials are mixed thoroughly and heated to a temperature of around, say, 1650 degrees Celsius in an oven to create a homogeneous melt. And you need to go this high because the main ingredient, quartz, has a melting temperature around this value. You then cool the molten mixture down relatively quickly in the shape that you require for the product. And this could, for example, be sheets, like in the case of ceramic cooktops. And during rapidly cooling down, you quickly pass the crystallization and nucleation regimes. You would slow down the cooling rate a bit around the glass transition temperature to avoid high stress levels in the product, and then cool down to, for example, room temperature, where you would cut the sheets into the right size. But this process only produced a semi-finished product that does not have the correct physical properties yet. Essentially, we've just made a glass with a rather exotic chemical composition. The actual glass ceramic is made in the second part of the process, which involves the ceramic conversion of the glass. Starting from the semi-finished intermediate, the glass is gradually heated to the nucleation temperature and kept there until a sufficiently high concentration of nuclei is created. And once the concentration of nuclei is sufficiently high, the temperature is raised to where the rate of crystal growth is high. And all we have to do is keep it at this temperature until sufficient glass is converted into a crystalline phase So in this way we can in principle tune the material to a very specific CTE. One of the problems in developing a glass ceramic is the high number of degrees of freedom, not only in the exact temperatures and dwell times that are used in the firing process, but also in the concentrations of the ingredients that you can add, which means that developing a glass ceramic that can be industrially produced requires very elaborate testing of temperature and dwell time tolerances and material compositions. Now let me quickly show you what the crystalline phase looks like. And for this I will mildly etch the surface of a piece of polished ceran using buffered oxide etch. After etching for about 1 minute, we see that the etchant attacked the surface, and when placed under a microscope we can clearly observe many small crystals in the etched areas. The size of the crystals is approximately, say, 4 to 7 microns, which is actually way larger than I expected them to be. Here I plotted a height map of the etched surface, illustrating the size of the crystals and the height that they stick out of the rest of the surface. In this case, the 2 crystals shown in the plot are about 6 to 7 microns wide and stick up around 0.6 microns. I also performed the same procedure with 0-dur, and here the crystals are definitely much smaller. These 2 images have the same scale, and I estimate the crystals in 0-dur to be around 1 micron in size. Now I was kind of surprised by the size of the crystals in general, and that is because they don't really seem to cause a lot of light scattering. 0-dur is not intended for transmissive use, but it is actually quite transparent, and in the case of ceran, the dark color is actually due to an additive. And it's only when you use a high intensity light source like a very bright LED or a laser that you observe scattering in these materials. Anyway, both materials are far from opaque, and with crystals in the order of the wavelength of light or somewhat larger, I would have expected way more scattering. Now let me illustrate why that is using a short simulation. To the left you see light waves going through a homogeneous medium, and to the right a simulation of what could happen when crystals are present that have a size comparable to the wavelength of light. And you observe that in the latter case light is scattered in all directions. Now there are 2 ways that you can avoid this scattering. The first one is by making sure that the crystals are much smaller than the wavelength of light. And the second one is to produce crystals that have a very similar refractive index to the rest of the medium. And given the measured crystal size, apparently the latter must be the case. Okay, that's all I wanted to discuss today. In the video description I will place a reference to a very good book that contains a ton of additional information. So if you can't get enough of this subject, get your hands on this book. It's good stuff and should keep you occupied for quite a while. Thanks for watching.